Alright, calculus, we're back here with the second part for this economic optimization. So we're trying to minimize costs and maximize profit. So I see the word cost in this next one. So we're going to be looking at a lot of the costs and how to minimize that. So let's see the situation we have. First, we have a closed box. So that means we got top, bottom, and all the four sides. And it's got a square base. That's why it says x by x here. And the volume is equal to 1800 inches cubed. Well, the volume of a rectangular prism like this one is just length times width times height. And we got length, width, and height. So that's going to be x times the height is y. So that's our volume. And if I look at this, I also know what the volume is going to be. It's 1800. So 1800 equals x squared y. Now, as we're thinking about that, a note that I'd like you guys to make is the idea that when you have constants equal to your variables, that's probably going to be your secondary equation. So this is our secondary. Let's look for our primary, our first equation then. This is probably the cost equation that we're trying to evaluate here. So our cost is going to equal, let's see, the material for the top and bottom of the box. So it's going to be the top and bottom. So it's going to be 2 times the base, the area of the base, which means the top and the bottom, times the cost per the base. So this is the cost for the top and bottom. And the cost for those is $3 per square inch. The cost for the sides, well, there's 4 of those, times each side, times how much is it per square inch? Well, it's $1 per square inch. So let's kind of simplify these here a little bit. The area of the base here is x times x, or x squared. So that's going to be 2 times 3 times x squared, or 6x squared. And the side is x times y, which is going to be 4 times 1, which is 4, and then 4xy. So the total cost is going to be our first cost plus our second cost, which is 6x squared plus 4xy. Now, that's actually not too complex of an equation there, but the fact that I have an x and a y in here means I got to get rid of something. So I got to get rid of, let's say we get rid of the y. We know that if we solve this other equation by dividing by x squared on both sides, we'd get y equals 1800 over x squared. So I'm going to take that and plug it in over here for y. So that means we'll have 6x squared plus 4x times 1800 over x squared. So we can simplify a little bit here. 4 times 1800 is going to be 7200. This x is going to simplify with one of the x's on the bottom, so then we have 7200 over x and 6x squared. Now, just to make this a little bit more friendly for derivatives, I'm going to go ahead and take that x, and instead of writing it in a denominator, I'm going to write it in the numerator to the negative 1 power. So this is our cost function. We'll call it c of x. We want to find c prime of x. Find that derivative and then minimize it. Okay, so 6x squared becomes 12x, and 7200 x to the negative 1 is going to be minus 7200 x to the negative 2. So we're going to move this 7200 x to the negative 2 to the other side, because we're going to actually be setting this equal to 0 here. 12x minus 7200 over x squared. Move that over. Then we'll have 7200 over x squared equals 12x. I could divide both sides by 12 and multiply both sides by x squared. And 12 goes into 72 6 times, so this becomes 600 equals x to the third power. At this point, we're just going to take the cubed root, or raise both sides to the 1/3 power. And that means the cube root of 600 equals x. What would that actually be? Let's see if we can figure it out or calculate it here. Clear, clear. So we got 600 to the 1/3 power. It's about 8.4343. Is approximately our x. Now, if we wanted to figure out y, what is the minimum total cost? Okay, so we got to actually plug that in. Oh, we could plug that in. So we're going to figure out what that is. Let's see. This is x times, so this is the c of x. That's what we want to plug in. Let's do that into our calculator here. So we go to our y equals, and we'll clear this piece. We're going to have 6x squared plus 7200 divided by x. And we're looking for a maximum or a minimum right around 8.43 most likely. It's probably where it's going to be, not considering endpoints. So let's go ahead and calculate that, but our window is probably going to go from 0 to, I don't know, 20 maybe. We can make our x scale 1. That's not a big deal. Now for our minimum maximum volume, it's probably not going to be quite that big, but let's say we'll go to up to 1,000 at most. Oh, whoops, that's going to be our 0, so clear that one, and we'll make it a 0. 0 to 1,000. And we'll go by a scale of 100s. Let's see what we graph. So we're not even getting anything here. Let's look at our table, see what values we get there. So we got huge numbers. Those are huge. All right. Well, in that case, we need to be doing values that are around 4,000, up to 4,000 here. So let's go back. So we need to go up to 4,000. And we can go in increments of 500 to kind of make it a little bit easier for us to see. There we go. Looks like we do have a minimum right about here. So I want to calculate what that minimum is. I'm going to do second and then calculate the minimum. I know it's right after 8, so I'm going to type in 8 for my left. And let's type in 9 for my right. Let's see if we get the same thing. We'll say 8.4. So it is. It's 8.4343, but the key here is that y value. So I'm going to drag this over. Minimize that there for a second. Let's take a look at this picture. So that minimum value there, right here, x equals 8.4343, but more importantly, c of x, or the cost, is equal to 1280.48. So that is c of this number is equal to approximately $1280.48. All for a box. $1,200 for a box. That's pretty crazy there. Alright, let's look for the next one here. Example number 5. Okay, now we've seen this one quite a bit. This idea of we have, we're traversing some difficult section, and we got a horizontal and vertical, but we're going to travel a little bit through the hard stuff first. We're going to do this red piece of travel, then we're going to do this blue piece of travel. So let's think about how this is put all together. A telephone wire is to be laid from the telephone company to an island 7 miles offshore. But the problem is the telephone company is right is not right near the island. It's 12 miles down the shore. So what we need to do then is figure out the cost of the red, so the cost over the water, and then we also need to figure out the cost on the ground, on the shore. I guess I should have put the water as a blue, but oh well. Let's work our way through this. Now we already have it split up here, but let's do some calculations just to see what we would do. If we have 0 for x, then that means our red length would go straight up and down, and that would be 7. Our land, 7 times, well, what's the cost? What is the cost for water? It's 300,000 miles, or $300,000 per mile. So it's going to be 7 times 300,000. And over here, the land would be 12 times 200,000. You put those together, we get 21 plus 24. That's 4,500,000. So 4.5 million. Now, if it was 12, well, that's the other extreme. That means that x would be 12. We'd go all the way over here. So land costs would be 0. But the other one, this would be the square root of 7 squared plus 12 squared. So we need to figure out what that would be. What's the square root of 7 squared plus 12 squared? That's going to be the square root of 49 plus 144. 49 plus 144. It's 193. That's going to be close to 14, really close to 14. So it's square root of 193 times 300,000. We're going to need a calculator for this. So we got second square root 193 times 300,000. What do we get? About 4.1 million. So 4.167733. 4.16. What was it after that? I already forgot. 7733. 7733. So almost 4.16 million there. 4.17 million. So we got 4,167,733 dollars. That's a lot of money. All right, so now here's the trick. We got to figure out what is the cost of the water, and the cost of the shore. Cost of the water is going to be 300,000 times the distance of the water. And then, so I'm going to erase this piece here and work out the blue. And then the blue is going to be 200,000, because that's the shoreline, times the distance of the shoreline. Let's see what we can find out for that. Okay, so if this is x, then that means this shoreline distance, which is right here, is going to be 12 minus x. And similarly, this distance under the water is going to be the square root of these two pieces, the 7 and the x squared. So 7 squared plus x squared. Okay. So we got those two pieces. Let's start actually calculating these. We're going to make some more space over here. Erase these pieces. So the red is going to be 300,000 times the distance under the water, which is the square root of 7 squared plus x squared. And then for the other piece, that's going to be 200,000 again, times 12 minus x. Alright, so let's look at the total. The cost total is going to be the seawater plus the cost of the sea shore. So let's plug that into our calculator. We're going to use the y1, y2, and then combine them. So for the first one, y1, that's going to be 300,000. So 300,000 times, now here's where we got to put the stuff in parentheses here. We got square root, second square root of 7 squared is 49 plus x squared. Okay. Now for the other one, it's 200,000 is the cost per mile times, now we've got to put this piece in parentheses. The other one we didn't really need to because it was built into the square root. But this is going to be 12 minus x. So now for y3, we're just going to combine those two. We tap on the vars, y-vars function. It's going to be y1, so you can press the 1, plus the second one, so that's vars, y-vars. Whoops, keep it on function. Now we're looking at y2, so you can scroll down and press enter or just press 2. Now I'm going to turn off the first two, but I was showing this in class actually. Let me go ahead and graph these. Let's look at our x values. So our x is going to go from 0 to 12. 12 is the biggest it can go. And for a y value though, that's going to be huge. We started out at like 4.5 million. We're getting down closer to 4 million. So we're probably going to go even lower than that. So we're going to start out, let's really hone it in here. We'll start out at 3 million. And then we'll do up to 4 million. And we got to go in increments of pretty big numbers here. Let's talk 100,000. 1, 2, 1, 2, 3. All right, graph. Okay, so I think we're even going to go lower than 3 million. Oh, that's what I was looking at. We're looking at the 3 different calculations. Okay, let's go down even lower here. So that means that we're going to have, let's go to our y values. We're going to take this, I'm going to delete that and make it a 2 million. There we go. Is that 20 million? No, that's 2 million. That's good. Alright, so we got that one, this one. Now this is kind of interesting because we're hitting a minimum over here, but they intersect over here. So we're trying to hit the minimum cost here. So let's see what we can do with that. The total, which we just added those two together, that minimum cost happens around that spot that we were looking at, right there. And then what we're looking for is to minimize that. So I'm going to turn off the first two. We want to keep them calculating, but we don't want to print them out on the graph. So we're going to press enter on the equal signs. And when we go to the graph, we should just see the one that we're looking at. Okay, this is the one we're trying to minimize, but let's go even higher than that. So we went from 0 to 4, 2 to 4. Let's go from 2 to 5. We need all these millions. Okay, so we're looking right here in the middle. Let's see what we can do to calculate that. That means we need to calculate a minimum. So I'm going to do second, calculate a minimum, which is 3. Now I'm already to the left a little bit, so let's just give a left bound there. We need to move to the right of the center. We got to move past the center because if we're just at the center, it's not going to be really strong enough for us. And then select somewhere here in the middle. That looks good. Looks like at about 6.29, and the cost is going to be just under 4, 396.5247. So the cost is equal to 396.5427, I think. Let's double check that. Yep. So that's the cost, and x equals 6 point something. It's 6.2609. And that's in terms of miles. And this is in terms of money. So here we go. At this point, this should be a kind of familiar problem. But the difference now is we're multiplying things by a cost. in order to calculate total costs, you got to figure out how much does it cost for one section. And it's usually a section of the measure times the cost per unit or something like that. Okay, let's look at the last one here. Okay, a small television company estimates that the cost in dollars of producing X units of a certain product is given by this. Find the production level that minimizes the average cost per unit. Okay, now right here it just said average cost per unit. That's kind of different because just a moment ago it said that the cost in dollars of producing, so the cost to produce the product cost total is equal to this. Let's call this C of X. But when you divide that by the number of units, which is the number of TV units in this case, that's going to equal our average cost per unit. So that's what we got to do. We got to take this and divide it by the number of units. Well, how many units are there? Let's see. If we're doing units, and that's 100 of them, and the cost, we got to plug in 100 into this. So we got to do a table. So I'm going to go ahead and clear this, and clear this next one. So we're looking at the cost is going to be 800 plus 0.04 times X plus 0.00002 times X squared. So we want to look at our table, but let's set our table so that we can plug things in. So if I go to set table, and it's going to be an ask. Excellent. Whoops, I want the table, not the graph. Here we go. So I want to ask. And so I got to delete all these numbers. I want to plug in 100 units. And while I'm at it, I'm going to plug in the other two as well. 1,000, or the other 4, I guess. 3, however many. 1,000 units. Then we're looking at 5,000 units and 10,000 units. So we have, now if I drag this over here, we have this much, but then the interesting piece is the average cost. So if this is 804.2, the average cost per unit, I'm going to divide that by 100. It'll become 8.042. Similarly, for the next one, it says 860, but now I'm dividing by 1,000, so that's going to be 0.86 per unit. Significant decrease there. And then if we're looking at 5,000, that was 1,500. Now we're dividing 1,500 by 5,000. How much is that? 15 goes into 50, let's see, 3 over 10, 0.3. This is going to be 0.3 if you calculate it. And if we're doing 10,000, that's 3,200 divided by 10,000. So we got 1, 2, 3, 4 zeros. We're going to move over 4 places. So this is 0.32. So it looks like now we're starting to go back up. We went down, and then now in between these two we went back up. So somewhere around here, around 5,000 units, we're hitting a minimum cost per unit. Well, I have an idea. We can actually calculate a second function that does the average cost. Well, so that's the total cost for all the units, but all we have to do is divide that by the number of units, which is X in this case. So then C of X divided by X equals the average. So let's do that. All I'm going to do in here is type in y1 second, or not second, vars, y vars function, and y1, and then I'm going to divide it by x. Now again, if I were to look at my table, I should get, oops, let's look at the table here. There we go. 8.042, 0.86, 0.3, 0.32. Now those are the numbers that we were coming up with our average cost. So that makes sense. All right, so now let's calculate the minimum of y2. So I'm going to turn off y1 on the printing. It's not going to print out on our graph. But we are going to look at it here. And if we look at our x and y values, we're looking at up to around 5,000 units is where we need to be looking. So this is going to be from 0 to, let's say, 10,000. We're going to count in increments of maybe 1,000. And for our y values, we're looking as high as 8, but as low as 0.3 over 2. So we're going to start down at 0, maybe go up to, let's say, 10. But we need to increment this every 0.5 or so. Try and estimate it for ourselves. Okay, let's graph it, see what we come up with. Well, that's interesting. It looks like we're hitting a big number here. Let's double check our window. We went from 0 to 10,000. And it looks like maybe we're flattening out at about 0.32. But that's kind of hard to measure there. Let's see if we can hone in right around that 0.3 and 0.32, see if it actually does go back up. So for our y value then, we're going to start at 0.29 and go up to 0.35. We're going to increment every 0.1. Now let's graph. We definitely hit a minimum right about here. So now all I did was zoom in on that 0.3 area. So let's see where that actually is. We got to do second, calculate a minimum, which is 3. That's definitely on the left side. Now I just need to go to the right side. These are in increments of 1,000. So we're looking at, that was 5,000. Then we got 6, 7. How about 7,000? 7,000. Now it looks like it's right at about 6,000. The average cost, ooh, it's really hard to see that. Let's drag it in here. See what we can see. Looks like it's point something 9298. Now, how could I actually calculate that? Well, I can plug in 6324 into the equation. But in order to get a better view, we'll zoom down even more. So we're going to have our window. And for our y minimum, let's go down to 0.25. There we go. That's definitely going to give us some room to see that calculation. So we're going to calculate the minimum. 5,000 is fine. We'll go 7,000 for the right bound, just like we did before, and we'll guess that's about 6,000. .2929. So that's an even better picture. We'll put that on top of this one. There we go. Find the production level that minimums the average cost per unit. So the production level X equals 6,324 units or 6,325 units. Why do I round it off? Roughly, where we haven't done it before? Because if you're looking at this, you're talking about individual units. You can't produce half of a product, or at least not in this case. They're an actual product, so we got to do either 6,324 or 6,325. Either way, we would just kind of compare those two and see which one would be higher, which we could even do. Let's go to our table. Let's do this exact. So if I go to my table and I type in 6324 and then I type in 6325, wow, we are so close that it's literally probably not even worth picking one or the other. So either one would work for us. Awesome. Okay, so that's it for all this economic optimization problems. You need to watch again and again and again and again until you get it, and then you say, yay! We're number 1. Cool. Have a good day.